Our sun, it continuously emits streams of high speed, high energy particles called the solar wind. Fortunately, we don't have to worry about it because the Earth's magnetic field acts as a shield and deflects the solar wind that heads our way. Even though the solar wind is deflected, it still has an interesting way to slip into our Earth's protective magnetic bubble called the magnetosphere. To understand this, I need you to think about the day you spent at the beach. It's a nice sunny day, and then the wind is blowing at you at a high speed, and the ocean water is coming at you towards at a slower speed. This difference in speed is what leads to the formation of waves in the ocean, and something similar happens in space. The solar wind is fast flowing, whereas the particles in the magnetosphere are slow moving, and this leads to the formation of waves at the boundary separating these two regions. As these waves grow, they eventually form rolled up vortices, as you see over here. These vortices mix the particles of the solar wind and the particles of the magnetosphere, and in this way, the deflected solar wind can slip into Earth's magnetosphere. Now, here's where things get interesting. As these vortices mix, they also heat the particles. As a result, the Earth's magnetosphere is 50 times hotter than the solar wind, even though the solar wind comes directly from the sun itself. A similar temperature mystery takes place at our sun too. While the surface of the sun is about 6000 degrees Fahrenheit, the outermost region of the sun, called the solar corona, which is shown in blue over here, is at an astounding 2 million degrees Fahrenheit. The first time I learned about this, it completely blew me away. It revealed a new complexity to nature that we weren't even aware of and challenged our understanding of the universe. In my research, I try to understand how this type of heating takes place and where does it get the energy to heat things to such extremes. To understand this, I study the fundamental processes in space that leads to this type of heating and temperature discrepancy. I study these processes by analyzing data from NASA's MMS mission, which consists of not one, but four spacecrafts designed to fly right through these vortices and collect data. Now, we will never be able to send a spacecraft to the solar corona. That will be like trying to heat a marshmallow at a volcano. However, by studying the heating that takes place right here and various other space phenomena that take place right here near Earth, we gain insights into other parts of the universe that we will never be able to go to, starting right here at our own sun. Thank you.